All right, so we're going to, actually, this is a bit, it's similar to object-oriented programming, actually. Here we have some particles, and let me see, this is actually starting a particle system. Can we actually do this as an object-oriented way? Let's see. Particles, strings, floating. Maybe floating has it. It's a bit more complicated. Maybe this would be a bit simpler. So what we have here is a particle system. And it's defined as system. Then we just add particles to it, and then we let the system run. So these are the two functions. System is defined as a new particle system. So let's look at what that is. Here, let particle system equals function position. It takes in a position and it finds an origin and list of particles. Then it adds a particle as a function to the origin. And then it makes it run, which basically means we just get a list from the particles, run this function, and splice it, basically takes it out of the list. So this part is belonging to the particle system. Whereas this part belongs to the particle system. So let me write it this way. Particle system. This part belongs to the particle class. It's written here, actually, a simple particle class. So what we could do is actually a few things based on this. So we can make it in such a way that random particles are spawned on the screen and they move in random directions. We can try to do that, or see how we can actually do it. So here, for instance, it says system that add particle. So what if we add a particle at a random location? So let's look at where that is. This dot particles that push new particle, this dot origin. So this dot origin is basically the origin of the particle system, which is the initial position. But we can make this random, actually. So if I make this, for instance, let's create vector. Actually, let's do it like this, extend the bit that x equals random width. That's y equals random height. So I'm just going to pass in a vector, random vector for the x and y location. Let's see what happens now. So now we got random particles spawning on the canvas. Okay, and then how do they move? So we run this function called p.run. So let's look at what that does. So the run function is located here, particle prototype.run. It's defined as a function. It's calling these two functions, this.update and this.display. So one of them is updating the location of the particle, the other one is displaying it. So update is here, display is here. We can actually make each of them have a different color if we want. For instance, when we spawn them, we define an acceleration, velocity, position, lifespan. We can also make this dot color. Let's give them a different color. This dot C equals color random 255 00. they're going to have a tone of red, each of them, and I can use this to fill them. So here, rather than doing fill, I can actually make this. It also has this dot lifespan. Maybe we don't use that. We just do this dot C. Yeah. So what's going on is actually we have a particle class which takes in a position to create, right? So if I want to create a new particle, I just pass in a position to it. And this position gets used for its position here. So anything that you're seeing with this dot acceleration, this dot velocity, these are variables that are stored in a particle object, okay? So I can define as many parameters here as I want, and they can all be customized per particle. So here, for instance, we are getting more and more spawn, and they're getting random hues. So I'm basically overriding a visual parameter here. I also randomize the position. We also have this velocity. For instance, velocity and acceleration. It's actually going in different directions. You can also make this go in all kinds of directions. Let's see. Acceleration, velocity, and how does this update work? So we first update it, and then we display it. Update basically adds acceleration to velocity and updates the position, and then decreases the lifespan, right? So what if I don't decrease the lifespan? Okay. If I don't decrease the lifespan, they're never going to be taken out of the simulation, but they're getting out of the canvas, right? So what if we make them in a way that they're just moving? They just move. Let's say that we want to have a movement like this. So I have a particle, I want it to move in a straight direction. And then when it comes to the boundary of the screen, I want it to bounce, right? So we want it to keep bouncing and bouncing and bouncing. So how do we do that? Let's actually try to do that, okay? So particle system, we're not going to use an origin for it. We're just going to create a list. We're going to spawn random particles. It's actually slowing down because we have a lot of particles spawning. Let's actually make it just one. So here, system.add particle. I'm just going to add one particle. And we're just going to observe the movement of one particle on the canvas, okay? Let's actually make it start at the origin, which is going to be, let's see, let x is fine, let y equals 0. So it's going to spawn at top of the canvas, and it's going to move in a random direction. So they're actually not moving in a straight line, right? So they're actually translating. What if we don't add acceleration? So let's take out acceleration. We just add velocity. So it's just moving. And we want velocity direction to be always facing down. So let's make it 0. Actually, let's make this -1. This is 0. X, Y. Oh, maybe we should do this. Would be 1. So it's moving at a constant speed downward. All right, so what if we do 10 particles, 10 random particles? So let count equals 0, while count is smaller than 10. Count plus equals 1. Let me stop here actually and see if you have any questions about what we are doing. So two things. We have a particle system, which basically manages a group of particles. And we have a particle class here. So we are looking at how these functions are defined and how they run. So a particle is defined as an object. It stores acceleration, velocity, position, lifespan, and I added a color to it. So every time I write this dot, it basically is written inside the object. And then we run this function called prototype.run, which basically updates the location and displays the object, right? So this is the particle class. It's actually, where is it? It ends here, right? So this is end of particle class. It's actually here, end of particle class. This function takes it out. And this is the collection of the particles. So what I did was I created 10 random particles at the top of the canvas, and they're all moving down at a constant speed. They're at different speeds right now. I initiate them with different speeds. This dot velocity, we are creating vectors. Y vector is defined as up to 5. So it's always facing down. So it's a vector like this. So what I'm doing is at every frame, I'm adding this vector to the location of the particle. So particles are moving down. Next thing I want to add to this is when they reach here, I want the velocity to be reversed, right? So I want it to keep going the other direction. So let's see how we can do that. So for instance, we have this dot position that adds this dot velocity. What if we check for the position here? For instance, if this dot position dot y is greater than, let's say, height, then what we want to do is reverse this dot velocity. This dot velocity dot y times equals -1. This will reverse it. We can also do an OR function here. How do we write OR? Let's find the symbol. It's this logical. So I want to check if the position is greater than height or less than 0. Let's see what's going to happen. Right, so now they're bouncing up and down. So next up is I want to make it work for left and right as well. So we can make it pretty straightforward. Actually, I can just add one more here. So just check for the x. If x is greater than width or less than 0, then we multiply the x of the velocity by -1. What this does is it basically reverses the vector, right? So if an object is coming to the boundary of the canvas, if it's sitting here, what we want to do is this is its vector, right? I want to get its x component to be reversed, right? So this gets reversed. And what happens is when the object is here, instead of going this way, it goes this way, right? Because I'm reversing x. I also want to do it for here, for instance, if it's coming like this, I want this to be mirrored. So we are going to mirror, in this case, the y vector. This is y, this is x. So when we flip y in the negative direction, it becomes this. So let me show you some vector functions. So if this is a vector, let's call it v. This has an x component and a y component, right? Right now, our objects are only moving in vertical direction, so we are only initiating them with a y vector. So if you look at here, for instance, we have x component of the vector is 0, y component is between 0 and 5. So that's why they are moving in different speeds in the vertical direction. And what I'm doing is when they hit the bottom, I'm flipping the y direction, right? So they're coming like this. This is their y vector. When we are in this position, I'm reverting their vector. So they go in the other direction and then they move like this. When they come here, I reverse their vector. So that reversal is happening here. So I'm checking if the location is greater than height or less than 0, right? So beyond this line, the position y will be greater than height. Beyond this line, it will be less than 0. So I did the same for width. So now let's do the same reversal here. For instance, if I make them move horizontally now, they will bounce the same way. Right, so I'm spawning them at the top. Let me actually make it this to be 0, this to be random height. Make sense? I'm going to stop here for a bit, then we're going to do something a bit more cooler. Let's make these points of cyan. Is it like this? This is really slow. So let's make it a bit faster. All right, pretty cool, no? So now let's make it random for both directions and see what happens. Right, so now they're bouncing all around. Okay, let's increase the particle count. Let's make it up to 50. Make sense? Now what I want to do is draw lines between these particles. So I want to check for distance. Basically, what I want to do is, let's say that I'm looking at a particle and it's within a vicinity of other particles. So let's say this particle, we are checking for a distance. Let's call this R. So if it has other particles inside of its vicinity, I want to draw a line, right? For instance, I only draw a line to this one. I don't draw a line to that one because it's outside of my parameter or threshold. We can also define custom thresholds, but we're going to play around with this visually a bit. Do you have any questions up until now? Huh? No, pretty straightforward. So we have particles and a particle system. Particle is an object. It stores acceleration, velocity, position. And I added color, custom color. Particle system just updates the location of these particles and then it runs the simulation. Okay, so we can do all those things with these particles. Now, what I want to do is every time we are updating it, or let's say we are displaying it. Let's say we display. We do this under display. I want to check if there is another particle that is close to this particle. Okay. So here, for instance, what I want to do is we can go through here. Particle this dot particles dot list. So we can do that probably here under run. This makes them run and it takes them out if they are dead. We are not using that at the moment. But what I want to do is inside of the particle system, I want to go through the list of particles and check for their distances to other particles. I can also do it this way, by the way. When we do run, where's that? We run them here. We do an update and a display. I can also pass in the list of particles here. For instance, I can pass this dot particles as a list to this function. And then come up here, take it particle list or call it list. This takes in the list. And then I want to pass it to display. And inside of display, I want to take that list and I want to check. I want to go through that list. We can do it like this, or let P in list. I hope this works. And check if the distance of all the particles inside of this list are inside a threshold to this particle here. So we can do, for instance, how do we check distance? Can we look at distance? Is it built in as a function? Let's get the reference. Distance. Vector. Add, copy, subtract, division, magnitude. This calculates the Euclidean distance between 2 points. So if we have two vectors, we can type in dot dist to find their distance. So I can do something like this, for instance. P dot position dot dist dot position, right? This will be the distance between this particle and every other particle inside of that list. So I can do something like this, for instance. If the distance is within, let's say, 50, what do we want to do? Let's say we want to draw a line. Okay, and that line, let's say stroke. We want that line to be white. And we want to draw a line between P dot position dot X, P dot position dot Y, comma, this dot position dot X, this dot position dot Y. All right, let's see if this would work. Ready? Oh, it gave me there. What is it? Cannot read the properties of undefined dist. Didn't calculate the distance. But P dot position. I'm wondering if it didn't get this list as P. Let's say it's P. 0. Oh, okay. We couldn't iterate through this list. So let's do it the old way. Probably because it's an object. For let I equals 0, I smaller than this dot length and I plus plus. Let P equals this dot particles. This I. Let's try to do it this way. All right. Now we got it. So I'm basically now drawing a line in between particles based on a radius value. We can also visualize that radius, by the way. We can also do an ellipse with no fill, and stroke as white. Then we can take this out and do stroke weight to be 0.5, read it in, and make the ellipse to be 50. Right, so this will visualize my radius around the object. And if we have another particle inside that radius, we can draw a line to it. Right, so now you can see if an object is getting inside of that radius, we are drawing a line. Some of them are moving almost in cohesion. I'm wondering if these circles intersect, if the outer circles intersect there, we are drawing lines basically. All right, cool. Now we can add a few more things to this. We can basically make the particles really small. So make this like 5, and then make the stroke weight of this line kind of a function of the distance. So if we are inside 50, but if we are really close, then we can draw a really thin or thick line. Maybe we should draw it if the distance is too far. How can we do it? So we can do let D equals. So we're going to map the distance, which is this. So let's actually do let D equals. Let's calculate the distance. So if D is less than 50, then we want to get, let's say, an R mapped. So the normal interval for D is going to be between 0 and 50. We want to map it to the stroke weight between 0.1 to 2. And then use R as stroke weight. So if they're close, the line is thinner. If they're far away, the line is thicker. It could also be the other way around, actually. So if I make it 2, 0.1, we are reversing the mapping, right? So if they're getting closer, then the line is thicker now. I'm going to disable this. So we get this. Right, we can also increase this. Let's do 100. More particles. Slow. Let's get it there. Cool. Pretty cool, no? Square. Let's make this 500 by 500. Let's make it into a container. Well, the initial locations are kind of congested. So I'm going to initialize them at random locations. Yeah. Much better. All right. What else shall we do to this? Now we can work with particles basically. So we also had an acceleration function. Let's actually look into that. What if we had an acceleration and limit the speed? This dot acceleration. What if we start using acceleration? Shall we do it? We can also take them out. They can also have different lifespans. New particles can spawn. We can add a few other functions to this. Yeah, let's add them one by one. But I'm going to stop here and see if you have any other ideas or questions. Huh? You're feeding it to ChatGPT? Huh? You wanted to code it? Huh? It's reading my code though.
Daha çok yolumuz var.
You can use ChatGPT to write code. That's so fun. Let's make it a bit more interesting. We have different colors. So what if we do a stroke here with this dot C? So they all have different colors. Let's leave this. No stroke. Let's make it background to be 255 and this to be a tone of black. All right, I want to get into acceleration. Now let's look at one particle. This is our single particle. Let's try to add some acceleration to this and see what we can do with it. So this dot acceleration and this dot velocity dot limit 5. I think there was a limit function. Yeah, it basically limits the length of a vector, right? So we can limit it to 5. Now the acceleration is, now this is kind of bouncy. Let's actually make it more balls. Now they're all bouncing down because the acceleration is always pushing them down. We can also make them move to the cursor, follow the cursor. For instance, when we do update, we could do this dot acceleration equals create vector, this mouse x minus this dot position dot x, mouse y, this dot position dot y. Let's see. Now they're following my cursor, but they're not moving around, right? So they're colliding. Yeah, they're colliding, so they're congesting. So they're trying to move to my cursor, but they're all doing it the same way. Huh? No, we have to add a repelling force, right? So that they don't collide like this. So they move apart. But they will be moving like the voids. So there was another code here, walking. So this is basically, these are not following the cursor, but we can also make them go to my cursor. So this is another version of particle system. Let's not make this, and like we just take this out. Yeah, the acceleration is always facing down because we are actually making it start like this. So what if we make it random as well? Random -1, 1. And same for y. Let's see. Ooh, they all moved apart. I'll make this 0. Oh yeah, the acceleration is always constant, right? So it's always pushing it in one direction. We need to make it kind of randomized, actually. So if we make it 0, then can we update it? For instance, this dot acceleration dot add and add kind of a random vector here, random 1, -1, 1. So I'm always updating a random. So now they're all always accelerating and decelerating. but in random directions, so they can change directions now, probably. Let's actually look at one, see. Well, it doesn't seem like it's accelerating or decelerating. Let's see. Get the reference. There is that. So shall we do it this way? We can directly add to it. So this should work. If we always do it like this. Yeah, I couldn't get the accelerator to work, but maybe it's accelerating, but I'm limiting it. All right. Let's make one more thing, which is going to be, I want to spawn at random times, and I want to take out some particles after their lifespan is done. Okay. So each of them are spawned with this a finite lifespan, so we can make it a random as well. So 152, let's say 250 is the random lifespan of a particle. And we want to check if this particle is basically exceeding that lifespan. So this dot lifespan -2, or we can make it -5, so they're going to die a lot faster. So when this is negative, they're going to be pronounced dead. And when they are dead, they're going to be taken out of the particle list. Okay? Well, they all died pretty quickly. No? So when it's -5. So let's make it -2. So some of them are going to go away, right? We can also make their sizes relevant to their lifespan. For instance, this ellipse, we can make the lifespan as a function of it. So we can probably do the lifespan. Let r equals this dot lifespan divided by 10. And we can use this to visualize their radius. So the smaller they get, the faster. The smaller they get, that means they're actually going to die fast, right? Okay. So they're dying. And what I want to do is when we are running the draw, I want to add some more particles. So if frame count mod 50, so every frame count, 50 frame count, we want to add a particle to the system. Well, they're spawned at the random lifespan. Let's actually make this at every 20th. So we are taking out and adding in as well. But we are taking out faster, I think. Let's add faster. So we are adding faster and taking out slower. All right. That's it. I'm going to stop there for a while and see if you have any questions.